assistant professor of in the computer science department in the School of Computer Science. He's also affiliated with the Societal Computing program in the school's Institute for Software Research. Zico got his bachelor's degree at Georgetown, his PhD from Stanford, and joined us 3 years ago.
4 years ago, but I was on leave for a year.
4 years ago.
Four and a little, well, no, 5 years ago now, but
I
on
got it
leave
up
for
there
1
too.
year, so.
Zico Kolter.
All right. I have a,
Yeah, no.
okay, gotcha. All right, thank you very much. It's great to be here. And I'm going to talk today about energy and data. As Jerry mentioned, I'm in the computer science department. My main area of work is in machine learning. Machine learning is the study of computational algorithms for learning from data. And one of the main application areas I look at is applications in power systems. So before I begin, though, the talk is going to be about energy and data, but really another way of looking at this talk is it's really kind of about optimizing the right thing. And I'll talk about what I mean by that in a second. But by way of introduction, I want to mention another machine learning researcher of the past who, mid-career, decided that he actually wanted to switch gears a little bit and write a book, a general audience book about energy. And not in terms of an applications of machine learning like I work on, but just purely about energy. And he wanted to do this because actually I think, much like Karen said, he felt that the debate about energy was being dominated by kind of emotional factors. And he wanted to provide very simple quantitative analysis about energy at a very basic level that could kind of guide our intuition in much better ways. For those who don't know, the person I'm talking about here is David McKay. He was a professor of physics, actually, at Cambridge University. He also went on to be an advisor to the UK government on energy issues. He sadly passed away about almost exactly a year ago and 2 weeks. And he was very young. He was 48 years old. And in the time he had, though, he's made this sort of amazing impact on both machine learning. He really made some transformational impacts in machine learning, as well as energy, really in a completely separate area. And the reason why I want to mention David here is that he really did, his book in particular really did transform kind of the way I approached my career and kind of the things that I wanted to work on. So he wrote this book called Sustainable Energy Without the Hot Air. It's a very popular book. I imagine a lot of people here have read it before. It's also a brilliant title. I think it's just a fantastic title. And the idea of this book was that one of the things he did in the book was he sort of built these stacks of consumption and potential renewable generation. Now, you can, of course, sort of argue with how we came up with those numbers in particular, but they were really kind of compelling just in terms of going through the raw numbers of how much we really use as energy and how much we can generate potentially, even if we forget about the costs, from renewable sources. And so as a sort of I read this book in 2009 for the first time as a sort of in the latter half of my PhD. And working in machine learning, but sort of always having an interest in things like energy, I sort of really appreciated this book for the easy layout it gave. And it also kind of gave me a lens on which to approach new problems in machine learning. Because what I wanted to do was use data to actually help with these two stacks, right? So I think that traditionally energy has been largely viewed as either a purely physical thing or maybe a policy thing. But as with many industries, there is this sort of third pillar of information and data that's becoming more and more available right now that we should really use and exploit to try to see where we can either increase our generation from renewable sources, or sustainable sources at least, and then decrease our consumption. And so I spent a lot of time thinking about kind of different areas of research that I could go after in this space. And while I've worked on a couple, probably the one that I worked on earlier in my career the most was a topic called energy disaggregation. So I want to spend some time and talk about what this is and why I think it's an interesting idea, an interesting way to pursue the challenges of energy from a data-driven standpoint. The idea of disaggregation is that we want to take some aggregate energy signal, say the signal that comes out of your smart meter at your home, which are going up, still not at my house here in Pennsylvania, but there are a lot of them around the country. We want to take this sort of either hourly or maybe actually locally even a more higher frequency signal, and we want to break it down into its constituent components. Right? So maybe we say that this thing is made up of a washer dryer in some levels, of electronics and sort of providing a base load, kitchen outlets that come on and off. This is actually a coffee maker that's heating up water and letting it cool because it was left on, and then a microwave there. And the motivation for this, the reason why we want to do this is that this is a lot like thinking about kind of receipts from, say, going to the grocery store, right? So when you go to the grocery store, you get a receipt that shows you what you've spent on everything. And our current understanding of energy from our data is not like this, right? It's much more like as if we had a receipt where we only saw the final line item there. And there isn't a lot you can do to change your behavior here to actually get better at consuming less energy. And so what I really wanted to do was to provide much more of an actual receipt for people's energy consumption. And a lot of studies suggested that if you give people this information, it will actually help them consume less. And this has been by far, I should say, my most successful line of academic work. And I'm saying that, just trying to be objective there in terms of evaluating my work. So I worked in this for a long time. Among other things, I think that, I'm not meant to read this thing here, but it's just meant to be some of the papers we have on these things. Among other things, a lot of the algorithms for disaggregation were fairly ad hoc. They sort of looked, they were very heuristic in nature. And so some of the work we did was apply much more foundational probabilistic graphical models to the settings of disaggregation in order to sort of, and then also use techniques from what's called approximate inference to actually compute the breakdowns. And so that was a big sort of change from what currently used to go on. I also, and this is actually my most cited work here, I just collected some data for this problem. So I went to a bunch of homes, I put CT clamps around each circuit in the house and monitored some individual devices as well, and then also monitored the main consumption of the house. I just did that for some number of homes. I released the data, and this has been by far I released it in my little workshop, and this has been by far my most cited paper that I have. Just releasing data is a really good idea, especially if you strike upon a problem that other people then want to work on, and especially if your first paper doesn't do it very well. That way everyone else cites it, and they say that they're doing better than you. And then I even did some work on some precursors for deep learning methods based upon essentially a technique called sparse coding for disaggregation in a slightly different setting. So I did a lot of work in this area. And this is, as I said, sort of been my one of at least my, I think by looking at publications, sort of my most successful venues of research. But the problem is that I don't really believe this to help that much anymore. And so what happened? Why did I change my mind here? It's a good story I gave you, right? I practiced it a lot. I gave the story really well, and I have to say I don't really believe it anymore. So what happened? Well, first, a couple things happened. First of all, I went on leave for a year to work at an energy startup in the Bay Area called C3 IoT. They were previously called C3 Energy. And among other offerings, they actually do release a disaggregation product that I helped them develop. And utilities didn't really want to buy this. They sell software utilities, and a few people bought this, but this was by no means their biggest selling product, and didn't really seem to be something that customers actually wanted in this space. The second thing that happened is there's been a lot of follow-on work to some of those original studies I mentioned, kind of questioning that logic. Does this really help to provide people these breakdowns, either in real time or maybe just even offline? And it's much less clear, if you do a sort of a meta-survey of a lot of literature, it's much less clear that people actually have sustained behavioral change from just seeing their energy data, right? You can certainly, as I'll mention actually again, you can certainly do things like replace your lights with more efficient ones. Everyone should do that. Probably we all have at this point. But are there sustained behavioral changes? It's really not that clear. And finally, I go back to this receipt example, because while it's very cute and sort of appeals to us at a fundamental level, I don't spend a lot of time looking at my grocery receipts. And if you do, it's a very quick thing where you just sort of can buy one cheaper thing one time, and you kind of go on your way. Whereas, as I said, real long-term behavioral change requires a constant engagement with your consumption. And I wasn't seeing that happen, even in the people that we're giving kind of the complete system to, right? The actual full system to. I just wasn't seeing that happen. So what went wrong here? Why isn't this working? And I think this is actually a very common thing that I've noticed a lot in machine learning research, in my own and in other people's. And that is the full process we're going after is requires a very long series of chains to really work. So maybe we have some data like from a smart meter. We apply this to a domain or we apply some algorithms to it to extract something interesting from this data. In this case, we separate out the components of our consumption here. We give this to people, and we assume that they're going to somehow respond to this information. We hope they'll respond in a certain way. And then this will then impact the world as a whole, because they'll be decreasing their consumption by a certain amount, and that will decrease everyone's, or decrease emissions worldwide, or have other positive effects. But the reality is that all sort of parts of this chain can actually be quite difficult. So sometimes we actually don't even have the data. I mean, the data I was using there that I showed you before was second-by-second data from houses. And while smart meters do have those, they can emit readings that high, they require special hardware to do so. And so are people really going to go all and buy a $20, even $20 piece of hardware so they can have this data? It's not really clear if they're going to. It's also not clear if people really respond in the way we want them to respond, right? Especially long-lasting behavioral change. I'm motivated to do these things, and I didn't notice a huge change in my consumption after a long enough time, after sort of the initial excitement wore off, I guess I would qualify it as. And then finally, it's also not clear that even if this was, we do get the 5%, 10% decreases we see in a certain range of consumption, whether this is really the right chunk to go after in terms of impacting the global landscape of energy. So this seems kind of depressing right now, so I've been kind of a downer right now. And I'll also say that what we end up doing in machine learning, I think, is sort of, because these chains are not all the academic research I work in, right? I work in machine learning, I work in algorithms. What I end up doing is spending a lot of time just kind of tuning these things, right? And so we're getting better and better performance of disaggregation, but the rest of the chain kind of vanishes here, and it's not taken into account. Now, I should say before I want to get too negative on this, there are, I believe, some very compelling applications to disaggregation. I think things like system-level views of what type of consumption is going on right now from a system operator standpoint, so from a grid perspective, are actually very, very useful. And large buildings and commercial operators are actually much more motivated to address these things than just single residential users. So I think there are some very compelling applications here. But I don't want to address that right now, because what this actually kind of convinced me of was something a little bit more general. Because I think this sort of pattern you saw here is actually becoming extremely common all across machine learning. So you've probably heard of machine learning, right? These techniques that can identify what's in an image, can classify images very well. It can do all sorts of really amazing things. It can do text-to-speech better than we ever could with custom algorithms before. And so all over the place, we have these cases where we have some data set, we feed it into a machine learning algorithm, but the process doesn't stop there, right? As it didn't in disaggregation. What actually happens is that based upon this information, we actually make decisions, right? So we use a classifier, not just to classify objects, but we use it in a self-driving car or something like this, hypothetically, right? We use image analysis to make diagnoses in medicine, but of course, what we do with this, we make decisions based upon these diagnoses in reality. And finally, in energy, we do things like we forecast energy, but we don't energy consumption, but we don't stop there. We actually plan generation based upon those forecasts. And then finally, based upon our decisions, we now suffer some costs. Of course, it's not always a monetary cost. That's just the clip art icon for what cost is. But we suffer some costs, be it emissions, be it monetary costs, et cetera. And so I think something is actually fundamentally broken in the way that we apply a lot of machine learning algorithms in energy and elsewhere. And that's the fact that this feedback loop of improving algorithms, especially in machine learning, almost always stops at the algorithm. So we're always trying to improve the algorithm. Whereas what we should be doing is trying to optimize the entire closed loop performance of the system. So we should actually be using the final consequence, our final cost, to tune our model. Not just to make the model as accurate as possible, but actually to make the model work well when we make decisions based upon those predictions. Those might seem like the same thing, but they actually aren't. In machine learning, when we make trade-offs in these models, those two can be very different, and they can lead to very different total outcomes. And this is a general technique now that we developed. It's not quite this simple. There's a lot of sort of math involved in actually figuring out how you propagate error back through decision-making processes. But you can do this. It's a technique that we're calling task-based learning. And it's one that I think actually has application in energy very broadly, as well as really wherever machine learning is applied in the loop of some larger system, which, by the way, is getting to be everywhere these days. So just as a quick example, this is kind of a toy example. This is very new research, and maybe in 5 more years, I'll be standing up here talking to you about how this wasn't a good idea, and the next thing is. That's sort of the beauty of science in some ways. But as a very quick example, one thing we've been analyzing with this is energy generation, electricity generation, where we first make a prediction, a forecast of people's consumption, and then based upon this, we schedule generation. And then based upon that scheduled generation and the true consumption, of course we don't know until we actually schedule our generation, we suffer some loss. And again, this isn't really, these are toy examples here, so this is sort of a dimensionless quantity, but it should capture some notion of both the cost, the monetary cost, and the emissions of our generation. Essentially a penalty for overgeneration and undergeneration, and a penalty on how much we change our generation from time to time. Now, if we use traditional forecasting, so we try to make our forecast as accurate as possible in terms of the mean squared error, we get a loss that looks like this. Again, the actual units here are not important, but this is the rough shape. These are the late, in the middle of the day, you have higher consumption. This is in the summer, or the afternoon, you have higher consumption, so the loss here is higher. Whereas if we actually train our system to optimize the final closed loop performance of this thing, using this task-based learning, we actually can cut some of our consumption, some of our losses, some of our monetary costs by almost half in this example. Now this is, as I said, a toy example, but we are using real energy consumption data here, and this is using a real sort of state-of-the-art forecasting methodology. And so I think it's actually indicative of just how big a difference there can be in these two methodologies. So, hopefully, this is, again, just starting out this research. I'm very enthusiastic because I think that this is a pattern that repeats again and again whenever we see machine learning applied. And I want to come back to David McKay at the end here, because I think that in some sense, a lot of the problems we have in research have to do with sort of this emotional response that he mentioned too. So just like we're emotional about energy, we get emotional about improving our own algorithms, right, a little bit. And it's worth thinking about what the big impact of our algorithms actually are. And so one thing that David McKay mentioned, has in his book, is that every little bit helps. But this is, to be clear, this is not what he's advocating for. He advocates the exact opposite. He says a better motto for thinking about energy, and I would argue thinking about research, is that if everyone does a little bit, we'll only achieve a little bit. And so I think that it has been a valuable experience to sort of go through a research agenda, which frankly, I think, while having some compelling applications, did not have the application that I thought it did starting out in it. But somehow, in an admittedly very abstract way, also leading us to this sort of more broad and kind of general idea of how do we actually take the end goals of our algorithm and how do we encode that in the machine learning itself. I'm hoping this is going to be a fruitful direction to pursue forward, and I hope it can do more than just achieve a little. Thank you.